Okay, today we will be talking about non-equilibrium applications of Newton's laws of motion. Sounds like a mouthful. When an object is accelerating, it is not in equilibrium. So really all we're doing is we're doing the same type of problems, the same format basically, but now it's not in equilibrium anymore, so the sum of the forces are not equal to zero, but they're equal to mass times acceleration. So the sum of the force in the x would be equal to mass times acceleration in the x, or Newton's second law. And sum of the force in the y, or equal to mass times acceleration in the y. And in summary, really, what we're doing is we're looking at when the object is in equilibrium, really Newton's first law applies. So all the forces add to zero and nothing happens. It's at rest, it stays at rest. If it's moving at a constant velocity, it continues moving at a constant velocity. But if it's not in equilibrium, the forces don't add to zero, then it will accelerate. It's important to note, though, that one or more of the directions may be zero. So that you can have acceleration in the x and no acceleration in the y. So this equation would be equal to sum of the force in the x equal to mass times acceleration in the x. While this may be sum of the force in the y may just equal to zero if this acceleration is zero. Alright, so how do we solve problems like this? We basically do it the same exact way we did before, but we have to keep in mind that some of the forces may be equal to zero, or they may be equal to mass times acceleration in each direction. And we may have one more unknown because we have the option of having kinematic equations to solve for an additional unknown. But keep in mind that you need just as many independent equations as you have unknowns. So you can have something like sum of the force in the x, sum of the force in the y, and a kinematic equation, so you could possibly have three unknowns. Alright, so let's look at an example. You have a boat that's being towed by two tugboats, T1 and T2, and it's accelerating along this direction. D is the drive, the force of the boat itself being pushed forward, while R is the resistive force of the water pushing back. And those numbers for each of those are here. And what we're trying to do is we're trying to find T1 and T2. Now this is no longer in equilibrium because it's accelerating. And it's accelerating in this direction. So the first thing you have to do is determine which direction you should make the axes. Well, I'm going to make the axes in the direction of acceleration because that would be the simplest way to do it. Okay? And I'm going to draw a free body diagram. And here's my free body diagram. The resistive force pushing back, the drive pulling forward, and T1 pulling forward, and T2 pulling forward. And once again, we break our vectors into components. This T1 has a certain amount pulling up, T1 sine of 30, and a certain amount pulling to the right, T1 cosine of 30. An analogous situation happens down here with T2. Alright, so now we have everything, free body diagram. We broke things into components. Now we can sum in each direction. And it's also important to note that the acceleration in the y is zero, so the sum of the forces in the y will end up being zero. Okay, so here's a summary of what we have. Okay, we have T1, which is broken into components, T2, which is broken into components. We have the drive in the x direction, the resistive force in the x direction. So let's see what we can do with this. So here's our free body diagram again, so we can refer to it as we're building our equations. So in the y, we have T1 sine of 30, T1 sine of 30 pulling up, while T2 sine of 30 is pulling down. And that has to be equal to zero because only accelerating the x, not in the y. And it's important to note that T1 has to equal T2 because these are equal angles once again. Okay, so this problem is a little easier than I could have made it. I could have made each of these a little bit different angles, and then you wouldn't have been able to do the simple reduction at this point. And in the x direction, now the sum of the force in the x direction have to equal mass times acceleration in the x. So we have in the x direction, we have t1 cosine of 30 plus t2 cosine of 30. So in other words, these two pulling to the right, so they're positive, plus the drive pulling to the right, minus the resistive force pulling to the left, have to equal mass times acceleration. And the mass of the object is 1.5 times 10 to the 8th kilograms. All right. I'll put this back up here so you can follow along. Now we have some of the forces in the x again. Some of the force in the x are equal to mass times acceleration in the x. And I know that t1 is equal to t2, which is, I'm going to just replace it with t, so I can reduce this whole equation down to t cosine of 30 plus t cosine of 30 plus d minus r equals ma. And since these are both the same, I can reduce it down to this. And then I can actually solve for t. Now, if you need a moment to see how I did that and plug in the numbers for yourself, pause the video and take a look at it. But all these problems, whether they're equilibrium or acceleration, are handled very similarly. Okay? All right, that's pretty much it.